This is project 2 video number 2, the one in which I actually coded up. First thing I want to do is switch over to the pencil and paper part and fix something up. Right here, I get delta r divided by this fraction. At least that's what I meant to have. I got to put this in parentheses, this bottom piece. Yes. Make a little bit more room here. So here we go. Nope, but the denominator in brackets. Or I could have just brought that 2 up to the top. And this was t is equal to the sum of t array. Okay, got that fixed up now. Fire up the editor. And I'm going to call it function. I think I may have had a name for it over here. Get distance and time. So I just have to copy that. Rf comma t equals R f comma t. So that's R final. I think I'll put R sub f. Let's see what I use here. Use the lowercase, so I'll stick with that. I use the underscore for the subscript indicator, comma t equals get dist and time, and it had 5 arguments: QA, QB, M, VO, and yeah, you know what? Instead of that underscore, I'm just going to put the letter right after it. So I'm going to go with that for all of them. So RF, and then this was Q, A, Q, B, there was V0, and R0, and something else, the mass of the moving particle. So this was the charge of particle A, the charge of particle B. I think forget which one was which there. Yeah, QA is the fixed one, causing the potential at the location of B, and QB is the moving one. Alright, so QA is fixed, QB is moving. And let's make sure that's the way I got it up here. Yeah, particle B has got this velocity V, here's got velocity V0, A fixed, B moving. Alright. Then I'll put an AND in so I don't forget to give the function its end statement. And I'm going to hit a tab to get over there. Get a little indentation for starting doing what the function does. Then I just want to go back to lean on the outline that I made. So I got to set k equal to what it is. K equals 8.99 E9. It's that Coulomb constant. And then I've got my function statement there. Obviously the k equals comes after the function statement, but okay. Use equation 1 to get RF. Okay. Equation 1. Said RF is equal to this 1 over this stuff. I think I'll reverse the order of the denominator for no good reason. RF equals 1 over, and then there was 1 over R0, then plus, I think, 1 over R0 plus mv0 squared over 2 times stuff. M times v0 squared divided by a bunch of stuff in parentheses starting with a 2. QA QB times K. K times QA times QB. Close parentheses for that denominator, and then close parentheses for the big denominator. I think I'll put an extra space there so it's more obvious. Alright, MVO squared over 2, and then KQ. Okay. I think that looks pretty much like what I had here. And then it gives me RF, and now I need an array from R0 to RF. Well, I think I'm going to try n equals 100. Put that there, and then might have to change that, and it's something I'm playing around with. So R array, the array of R values, equals linspace of, or from R0 up to RF, and I'm going to have n values. So this creates an array. It's like a list of n values from R0 up to RF, equally spaced. Then I think I had to calculate the velocity. V array I'm going to get using equation 2 with R. Oh, I see. I was going to fill up V array all the way up to the next to last element using equation 2. And I can only use the first n-1 elements of R array. Okay, let's find equation 2. I guess I'll try to get started with that. V array of 1 colon n-1. V array of n of 1 colon n-1. So it's all the elements of the array except for the last one, and I'm going to assign them using what I call it equation 2, which is v is equal to v0 squared, that stuff. Well, it's got a square root. V is equal to the square root. V, oops, I'm going to square root of, I think I'm actually going to go dot. I'm going to go to the power of a half. So to the power of a half. So there's my square root, and v0 squared goes inside 2kqq over m, etc. Let's see how much I can remember. Not very much. v0 squared plus 2 times qa times qb times, I think there was a k. It was probably divided by, and no, divided by m, and then times the difference in reciprocals of the distance. Slash m times 1 slash r0 minus 1 slash rf. Let's see. R. So it's really R array. And I don't want the whole array, just the first n minus 1 elements, all but the last element. Alright. I'll put a little spacing there, just because I think it'll be easier to see what's what. So this parentheses right here is met. Here's the argument of the array, just the indices of the array, and then this parentheses matches this one, and then this parentheses is the whole thing that I'm taking the square root of. Alright, now here's the thing. I want this all done on an element by element basis. I've got things typed in as if our array, for instance, was just a number. To make it do it on an element by element basis, one element of that array at a time, I use a dot right there. Now, 1 over r0 which is what I wanted to have there, is just a constant, so I don't have to worry about the element by element basis. That r0 is just one number. And I subtract that, and then I'm going to multiply by all of this. Now, all these things are just single values. They're not arrays of anything. So I've got an array multiplied by a single value. That's no problem. And then I'm adding a single value, the v0 squared, to it. That's no problem. But now I'm raising the array to the power of 0.5, and what I really want to do is raise each element of the array to the power of 0.5. In other words, take the square root of each element and then assign the result to this other array, v array. So I think I've done all that. I want to just to play around a little bit in the command window. You can experiment with stuff. I'm going to make up an array called A equals, I'll go linspace 0, comma, I go 0.5, and I'll go 6 elements. As I think if I use 6 elements, it'll make it so that it goes 0, 0.1, 0.2, 0.3, etc. And I don't put if I don't put a semicolon there, then it'll print out whatever I just did. So sure enough, I got 0, 0.1, 0.2, etc. And then I want to show you what I mean by like A of 3, the third element in this array. I think I'm going to change my mind on that. I'm going to clear A and set A equal linspace of 0.1. And just have 5 elements. A little easier to play around with. Then A of 2, when I just type in the A of 2 without a semicolon after it. It'll just print the value of A of 2, and you can see that it has printed the value of the second element. So this is called the index of the array, and this is the second element of array A. 1, 2, it should be 0.2, and it comes out just fine. Now, if I want to deal with, say, all but the last element of A, I'll go A of 1 colon 4, which the 4 is the same thing as 5 minus 1 if I use an n here, for instance, so that I could change it later on. And you'll see it's just got the first 4 elements of it. Likewise, if I wanted to do A of 2 colon 5, it does skips the first element, so it does the last 4 elements. A of 2 colon 5, 0.2, 0.3, 0.4, 0.5. So that's the kind of thing that I've been taking advantage of, this nature of the arrays, where an array is more or less a list of values. And then if I want to say raise everything in A to the power of 2, I want to try taking the square root of it. That's something that I decided not to do. And it looks like that would work just fine. It looks like it takes the square root of each and every element, like 0.701, 0.707, 1 times, I'll just square that to the 2 equals 0.5. So I shied away from that, but I think it looks tells the reader a little bit, it makes it a little bit more obvious what we're doing if I use the square root. So I'm going to use the square root after all instead of the 0.5. And so I'm taking the square root of an array, where the array is this is the array, and it's subtracted from a number, and then it's the whole thing is the resulting array is multiplied by a number. That gives me an array. I add it to another number over here, and then I'm taking the square root of it on an element by element basis, and that's what it looks like that SQRT does. So if I run into problems, I can just put the to the power 0.5 back. Okay, let's get back to my outline, which I'm leaning so heavily on. The last one is going to be 0. And I remember why I did that. I was worried that I'd have something slightly different from 0 evaluating that equation under the radical, something slightly negative, and then I'd get an error. So I think that might protect me from an error. So V array of n equals 0. And we programmed it up that way so that when RF is the point at which the velocity is 0, that's the turnaround point, the closest point, or the farthest point that this charged particle gets away from the other charged particle, the one having the opposite sign of charge. So I do have to remember that QA and QB have to have opposite signs when I go to use it. The user has to know they have to have opposite signs. So I got the last element now. Delta R is R2 minus R1. Let's see. I'll call that dr equals R array element 2 minus R array element 1. So that's the spacing between the elements of the array. I could just say it's equal to RF minus RO divided by N. That would work too. I feel like doing it this way. Then T array of 1 is equal to 0. So now I'm starting to build up the time arrays. I've got a formula for it that covers everything except for the first element. So I'm going to call that Go ahead and type that in. T array element 1 equals, and 0, I think it was. And then T array element 2 to n is going to be equal to, I have delta r divided by that. I'm actually going to bring that up there, so I got 2 times delta r. In other words, multiply top and bottom by 2. 2 times delta r. 2 times delta r. And then divided by, and then that whole fraction there. V array of 1 to n minus 1 plus V array of 2 to n. Alright. Plus the same thing, V array of 2 to n. And gotta tell it, I'm gonna just put a little space in there. I think it'll make it a little bit easier to read for the human. Yeah, these are both arrays. I do the sum, I get an array. I want to divide that into a number on an element by element basis. So I need the dot in front of my division operator, so I do it on an element by element basis. And I think that'll do. I'll put these semicolons there so those numbers don't all get printed out. And semicolon there as well. So then T equals sum of T array. So my return variables were R, F, and T, and here's where I assign RF, and here's where I assign T. So let's test that out. I think I'll save it. That's the right name for it. I got to see where I'm saving it. Spring 2016. Projects, project 2. I think that's a good place for it. And then I got to get to that same location here. So my documents, a spring 2016. Projects, project 2, and there it is. So I want to try running it. Get dist and time of, and the arguments are up there. We'll go -1 e minus 6, 1 e minus 6. Make it like 5 grams, so 0.005 kilograms. And RO, I think I'll start it at 3 centimeters, so 0.03 meters. Let's see if we get an error message here. Not enough input arguments. So I got 1, 2, 3, 4. I think I forgot the distance. the velocity. So I had it 0.03 meters there. So let's try that again with a velocity of 40 meters per second. And it's given me one value. Which represents the final distance, and that's actually a negative value. So that's not working out too well for me. Let's put the whole thing in. I'll go, what is it, distance and time equals, I'm going to try hitting the up arrow there. Control C, Control V, 1, 2, oh that must have been a later try. I'm going to try 50. Oops. So same one except camera 50. I grabbed the wrong version of that entry. Alright, so getting a negative distance and an imaginary value for the time. So things are not working out too well for me. Let's see if I can see YRF first off would come out negative. Let's see if I typed it in right. So I think RF is from equation 1. And this is definitely negative because one of the charges is negative. So let's see if that makes any sense. QB is my moving particle. So I got kinetic energy in the before picture plus potential energy in the before picture equals strictly potential energy in the after picture. I solved that for RF. So imagine multiplying both sides by that, dividing both sides by that, and I would say I've got it looks good actually. So I'd say what's going on is this particle never comes to rest. So if I launch this with too great a velocity, as it gets further and further away, the attractive force which is slowing it down gets weaker and weaker, and in the limit, as the particle gets out to infinity, the retarding force goes to 0, and it's conceivable that if the particle was going fast enough in the first place that it never comes to rest. So there is no point where it comes to rest, and hence I think I learned something about my code. That is, if the velocity is greater than the escape velocity, then there's no solution to it. There is no distance that it gets to, and that's we can tell the reader that if the distance comes back negative, this means that the velocity is greater than the escape velocity. So let's try slowing this thing down. I had it at 50 meters per second. Let's see if it'll stop if I go 5 meters per second. And if that doesn't work, I think I'm going to lighten up the particle. So it's got too much momentum to start with. So here we get stops it in a very short time with that tiny velocity. I do want to check to make sure some things are making sense here. In particular, if I make it a more massive particle, well, I'll get it going faster, but hopefully not too fast again. I guess I'll risk that. Here, too fast again. The time went negative. I'm going to go, say, 15. Still, I shouldn't say the time went negative. The distance went negative, and the time became a complex number. We get this. This is an imaginary part to it. So try 10, and takes very, very little time to bring it to rest, which I find interesting. So get it going on, say 12. Number 15 was too much, and 11. So I think 10 worked. And get it goes 18 centimeters, and it only takes a tiny fraction of a second in order to bring it down to nothing. Let's see. If I make it a more massive particle, and I'll start it off going more slowly. Still takes 0.5 meters per second. So doesn't go very far before it stops it. Not very far at all. And then I find it a little surprising that it goes such a short distance. So that is a massive particle, though. And I think I like the 10 better. Alright, so interesting stuff in my opinion. If this is coded up right, and I think I ought to try to make some more checks on it. But if this is coded up properly, then there are aspects about it that seem just right. If you got it going too fast, there's not going to be any point really that solves this equation. And as a result, you get it gives crazy answers. I call it a negative distance. In other words, this is 1 over RO is a value, and we're subtracting off a value, and it says what does RF have to be? Yeah, this solves RF, but if the velocity is too great, this term, which is negative because one of these charges is negative, is going to be of greater magnitude than the 1 over RO, and so it's going to give us a negative distance, where that distance is supposed to be the distance at which it achieves zero velocity. So when I get a negative value for the distance, it's really telling me that it never achieves a zero velocity. And as long as this is the bigger term, where we can find a value that we get a positive value if this is the term of greater magnitude. Okay. I think what I'll do is call that quits. Oh, I do want to try changing the n. Let's see what happens if I double the n. I go 200 there, and save it. And then run that again. And I get 0.1810. And I got 0.1810 the last time. So by making smaller steps, I made a small change to the time, but hardly changed anything. I think I might leave it at that because it did change the time a little bit. Let's try doubling it again. Control S to save it. Up arrow, enter, 0.0619. So to 3 sig figs, we're getting the same thing that we got the last time, and the time before that we got 0.0618. So I'd say 200 values is actually enough. So I bump it up after that, and it doesn't change it. Remember, I need a lot of values in one sense because I'm making an approximation that the velocity as it goes from one point to another, that is 1/200th the total distance that it's going to go, the velocity during that time interval is a constant, and I set the constant equal to the average, the midpoint value, the beginning plus n divided by 2, but it's not really, I'd say the average of those two velocities, but it's not really the time average for the corresponding time interval. It's just very close to it, and the smaller I make the time interval, the less it matters whether it's exactly it or not, or just how different it is from it. Alright, so I got a set of values there. I would be interested in a case where it takes longer for it to slow down. Notice if I started it farther out, it would also tend to escape. So probably if I double that distance, for instance, I'll get that negative answer. Let's go. Let's try that. So I want to try doubling that. And yeah, I get the negative distance and the imaginary time, so I'll go back to the way I had it working there. Alright, let's call that a wrap for video number 2, the actual coding of our function.